Be magic.
Precisely. All right. Thanks everyone for coming. We're very happy to have Kevin here with an incredibly provocative title. So I'm looking forward to seeing what's up.
Yeah, great. Thank you. Yeah, thanks a lot for the invitation. It's really a great pleasure to be here, especially in person, meeting everyone. And it's been a long time since I gave an in-person talk without a mask on, so it really feels great. I don't have to work hard to catch my breath. So I'm going to talk about this recent paper, Magic Zeros and Hidden Symmetries, that I put out with my collaborators, Santa Barbara, Nathaniel Craig, Isabel Garcia, and Arkady Weinstein.
Garcia.
Garcia, yeah.
Accent, not Garcia, but Garcia.
Oh, I actually,
the accent
I'm probably pronouncing it wrong. Sorry.
No, sorry. I apologize.
Sorry.
All right.
Not Garcia.
Garcia.
Yeah, you can tell. Anyway. So here's an outline of my talk. I'll start with a brief prelude where I'm going to introduce some of the key ideas in a very simple setting, not particle physics setting. So basically the two main ideas which we're all familiar with are, first, symmetries in the UV will tell us about some selection rules in the IR. And second, even more generally, symmetry breaking in the UV can tell us about some selection rules in the IR. And this is actually what I mean by hidden symmetry. So for the rest of the talk, hidden symmetries will not mean like spontaneously broken symmetry, but explicitly broken symmetry in such a way that they can lead to some selection rules. So then I'm going to get into the magic zero that is the focus of this talk. So this is basically motivated by the muon G-2 anomaly, and there is a very simple model with a standard model plus vector-like fermions, where you find that upon integrating out these heavy vector-like fermions, you get a vanishing dipole operator at leading order. So this was a very interesting observation made by Nima and Keisuke last year. And then I'm going to talk about how to understand this magic zero from symmetry considerations. I'm going to give you two versions of the symmetry explanations, one in the mass basis, namely electroweak broken phase, and one in the gauge basis, namely electroweak unbroken phase. So let's get started. As I said in the prelude, I'm going to talk about a non-particle physics example that's really simple. So let's just look at a pendulum. And as we know, the parameters, the UV parameters of the theory are the length of the pendulum, the mass, and the gravitational acceleration G. And we know the solution to the equation motion would just be a harmonic function. And one simple example of a symmetry in the UV that dictates selection rules in the IR would be that we have time reversal symmetry in the UV dynamics. And this in turn means that in the observations that we make in the IR, theta t is equal to theta minus t. As simple as that. But there are also lessons we can learn from symmetry breaking. So this is a set of transformations where we scale space and time and mass and everything. This is not a symmetry because all of these are parameters of the theory, and they're constant. They're not supposed to. When you make this change, the theory does not stay. It takes you to a different theory. But this is exactly what we do all the time for dimensional analysis. And this is not a symmetry, but the way that this symmetry is broken is telling us something about what we can observe in the IR. For example, if we look at the angular frequency omega, we know how it should scale under this set of transformations. And this in turn tells us that there's a unique combination of these UV parameters that will give us the right result for the angular frequency. So this kind of analysis is known in our field as spurion analysis. Namely, we treat all these parameters as spurions, pretend that they transform under some symmetry, but really it's not a symmetry. The fact that these are just constant parameters means that this symmetry is broken. And exactly the way that this symmetry is broken is telling us something interesting about the IR. So we're actually going to see something very similar playing out in the particle physics context in the rest of this talk. So now let me get into the main part, the magic zero. So this is a very simple model, as I said, motivated by the muon G-2 anomaly. We just have a standard model plus some vector-like fermions. Actually, if this works, yeah, great. But I guess it's okay. Yeah, so standard model plus vector-like fermions. So we have SU2L doublet fields, LC and L, with hypercharge plus -1. So basically, L has the same quantum numbers as the standard model left-handed lepton. And we also have the singlet fields that we call SC and S. So these are two pairs of Dirac fermions. We can write down their Dirac masses. They couple LC to L and SC to S. And then we can write down a few Yukawa interaction terms. There are these two Yukawas, YB prime and YB, that would couple the heavy fermions to each other. And there are also two other Yukawa couplings, YL and YR, that would couple the heavy and light guys. Yeah, this is a model that people have looked at a long time ago, but it was recently brought to our attention by Nima and Kesuke in this very interesting paper. And actually, for the rest of the talk, I'm mostly going to set this YB parameter to 0. This is one of the heavy fermion Yukawa couplings. The analysis is very similar when this parameter is not 0, but setting it to 0 just allows me to simplify the presentation. So if we want to calculate the contribution to the muon G-2, very naively, the dominant contribution should come from this kind of diagrams. So actually, in the next 3 slides, I'm going to talk about how we obtain this magic zero in 3 different ways. So first of all, we can just do this diagram calculation, write down the value of this diagram, and because we're looking at the low energy limit to see what the effective operators are, we can expand in the external momenta, and at a relevant order, make this simple substitution. We find 2 terms that exactly cancel each other. So what this means is that instead of this diagram, which would be giving rise to a dimension 6 dipole operator in the unbroken phase, so the leading contribution really comes from some high order diagrams, say 2-loop diagrams, or with more Higgs insertions that would give rise to a dimension 8 operator. So there are other ways to understand this. A second way.
Can I just ask a question? So if you have here this H minus, is this a goldstone or?
Yeah, this is a goldstone mode. So you can do a similar calculation in the unitary gauge if you wish, using the longitudinal W, and the result is the same.
Okay. Okay. And maybe another question. Can one have CP violation in this model? Would this magic zero also mean that?
There is a physical phase. So there could be both a magnetic and electric dipole moment. So it's really just the dipole operator that we're interested in. This real part is the magnetic dipole moment.
Yes, right.
And the imaginary part is the.
And you say both of them vanish. You say both of them vanish.
Yeah, both of them vanish.
Okay.
Right.
So there is another symmetry that protects all dipole operators.
Yeah, and we can't really see it from this level, but it's exactly what the rest of the talk will be.
No, I mean supersymmetry.
Supersymmetry. Well, this is not a supersymmetric model. Okay, it could be, yeah.
I know.
Okay, so the second way to understand or to see this magic zero is this very interesting observation made by Nima and Keisuke that this can be recast as what they call a total derivative phenomenon. So essentially all we need to do compared to what I showed you on the previous slide is that we relabel the loop momenta. So shift K to K plus P plus Q. And then in the end, we see instead of just getting a zero at the integrand level, we get an integral over a total derivative. And because this vanishes at the boundaries, we get 0. So I mean, this is a very interesting way to understand this cancellation that has applications even beyond this case that they pointed out in this very interesting paper. And more recently, there has been a paper by Alex Pomeroy and collaborators saying that the same magic zero can be understood from a Nonshell viewpoint. So basically, they figured out a way to systematically extract EFT operator coefficients from UV theories using off-shell methods. Basically, for each of this kind of diagrams, you can decompose it into a sum of master integrals with coefficients given by the products of tree-level off-shell amplitudes. And for this case in particular, they were able to show in a relatively simple way that the only relevant cuts are these two particle cuts, and there were two of them, cut S and cut L. So cut S is just written as the integral over the product of these two off-shell amplitudes, and by calculating the amplitude this way, we obtain this expression for the contribution from cut S, and cut L is simply cut S with this simple replacement, and that's the way you see it. The two terms add up to 0 from this off-shell calculation. So yeah, I guess I've told you 3 different calculations that are all telling us that we get 0 because of some kind of cancellations or total derivative phenomenon. So this is really making it mysterious because it's not a symmetry explanation at this point. It's just by explicitly doing this calculation that we see a 0 in the end. So yeah, actually I'm going to bring up something else before getting into the symmetry explanation, which is the mass versus dipole operators. So we usually associate mass with dipole because they kind of have similar symmetry structures. So if we calculate the muon mass threshold correction, the diagram will be basically the same but without the photon. And we do this calculation, we find it's non-zero. So we have a non-zero mass, 0 dipole. Is this surprising? And in fact, it's not, because the mass and dipole actually have different symmetry properties. And the way to see this, let's consider a simple case of a Dirac fermion made of E and EC. Think of these as the standard model electron or muon. So we write down the kinetic term. It can be written in this way, and we can further put E and EC in a doublet that we call chi. So instead of E and EC dagger, we put E and EC in the doublet, and we can write the kinetic term in this way. So because we have 2 wild fermions, E and EC, the free part of the Lagrangian enjoys a U2 symmetry, U2 global symmetry. And we can further write it as a U1A cross SU2B, where under U1A, E and EC will rotate by the same phase. And the third generator of SU2B will be the U1B subgroup, which is where E and EC rotate by opposite phases. So this is the U1 fermion number. And then we ask, how do the mass and dipole operators break this symmetry? So they actually break the symmetry down to different subgroups. So when we write down a mass term, we can write it in this form using the notation I've just introduced. U2 is broken to just U1B, the fermion number. But the dipole moment actually breaks U2 down to a larger subgroup. The entire SU2B is preserved because the structure of the operator is such that it's epsilon ij, which is an invariant, SU2 invariant. So what this is telling us is that we can have different possibilities, right? So it's relatively simple to imagine that we can have 0 mass, non-zero dipole, just because the dipole preserves a larger symmetry. So that is telling us if the UV theory has an SU2B symmetry, if the UV theory has SU2B symmetry, then all we can generate in the IR would be something that preserves SU2B. So dipole is allowed, but mass is not. So this is an example of symmetries in the UV leading to selection rules in the IR. And this is something that was already discussed long ago by Vanishing. But the present case is the opposite one. We have 0 dipole, non-zero mass. This is harder to understand because, as I said, the dipole enjoys a larger symmetry. So the fact that we're generating a non-zero mass means that this SU2B must be broken. But then, why can't we also generate a dipole? Right. So this is actually an example of symmetry breaking in the UV leading to selection rules in the IR. And the way to understand this is that, as I said, we need to have SO2V breaking in the UV. We can introduce spurions to characterize this breaking. And then in the IR, the task is to put together these spurions to form a singlet that can be a dipole which preserves SO2V. And it just turns out the possibilities that you can put together these spurions is limited, and that is what makes the dipole vanish. So for the rest of the talk, I'm going to expand on exactly how this happens.
Right. So I just said actually the other way around is also kind of generic in a sense that if UV's theory had a symmetry and you're asking for some operator which requires a bigger symmetry, unless the breaking pattern is very special and unless you have enough ingredient UV such that you can assemble to generate the object with a larger symmetry, generically it's hard to generate, right? Probably you're saying.
Yeah, I mean, said in this way, it's kind of quite natural, right?
Yeah.
But it's just that, and it's not really symmetries dictating selection rules, but really symmetry breaking. Yeah, exactly as I said, it's not
Okay.
It's not unexpected.
Could this remind me of little Higgs type things?
Yeah,
Super.
I don't know. I
Okay.
don't have a complete example, but yeah.
Okay, all right.
I mean, in a sense, I was trying to say the breaking is also important information, right?
Yeah.
Not just the symmetry, but also how it is broken is also special information. It controls what kind of thinking.
Yeah, exactly.
Yeah.
Yeah, so as I said, I will get to the symmetry explanations for the rest of this talk. And there will be two versions of the explanation, one in the mass basis and one in the gauge basis. So let's first look at the mass basis. Yeah, so let me actually start with a toy model that's simpler than the full model, but we'll very soon see the connection between the full model and the toy model. So in the toy model, let's just look at two Dirac pairs of heavy fermions that are neutral, that we call psi and psi c, psi hat and psi c hat. For the light field, we have charged fermions, which will become the muons in the end, and also a charged scalar, which will become the charged Higgs, as we'll see very soon. But in this toy model, what we can write down are the Dirac masses for the psi and psi hat, and also a few Yukawa couplings between the heavy and light fermions. So because we have 6 wild fermions, the global symmetry is U6. After writing down all these mass and Yukawa terms, the symmetry is broken down to just the U1V, the fermion number. So it turns out that it's sufficient to consider just a subgroup of the full U6 symmetry. That is the 6 U1 factors. That is a phase rotation on each of the wild fermions, and also and exchange these two symmetry that we call P psi, which basically exchanges psi and psi hat and psi c and psi c hat. And what this means is that if we think of these parameters as spurions, we know how they transform under this subgroup. They will just acquire phases according to where they appear in the Lagrangian, and also the exchange symmetry will swap M and M hat, and basically each parameter with its hatted counterpart.
Can I have a question? I'm confused. Psi c is c time like charge conjugate of.
Well, I haven't introduced the charge conjugation. For now, it's just like these are different wild fermions. We can define charge conjugation to relate the two, but we're not there yet. Yeah, so now we integrate out these heavy fermions, and this will generate mass and dipole operators for the light fermions, E and EC. And the point is that the forms of these operators, these operator coefficients, are actually very constrained by the breaking of the U1 to the 6 times P psi symmetry. For the mass and dipole, we have dimension plus and minus 1 respectively. And we need to find a combination that is even under this P psi exchange symmetry, and also keep track of how these transform onto the 6 factors of U1. And also, because M is a renormalizable operator, there can be logs, but the dipole cannot contain a log. So putting together all these constraints, we are actually able to write down a unique combination for the mass of the dipole. And in each case, we have 2 terms that are related by this psi exchange symmetry. So basically, one term is the other term with the parameters hatted. So yeah, that was the story of the toy model. And the reason I started with this toy model is, first, it's a relatively simple context. And second, actually, the full model can be mapped onto this toy model if we focus on the neutral fermion sector. And the way this works is, again, write down the full model Lagrangian with the mass and Yukawa couplings. So we set the Higgs to its valve. We look at the electroweak broken phase. And there will be mass mixing induced by these Yukawa couplings. We need to diagonalize the mass matrix. And we need to perform a rotation in this way, as shown in these equations, with rotation angles theta and theta c in order to do that. And it's a very easily solvable system that we can get the rotation angles. And the way it maps onto the toy model is simply that after this rotation, the scalar will just be the charged Higgs, and the heavy fermions will just be the neutral components of the heavy vector-like fermions in the original model. And the mass and Yukawa couplings will in turn be expressed in terms of the mass and Yukawas and the mixing angles in the full theory. So now we have everything set up. We can just borrow the result of the spurion analysis in the toy model to see what happens in the full model. So in the toy model, as we saw, the symmetry breaking constrains the dipole to take this very specific form, the sum of these 2 terms. And then once we plug in these expressions, this will be the result for the dipole in the full model. So now the question is, how do we explain this is 0? So this is, instead of a magic 0, we're really talking about the magic relation. So if we have a way to show that this relation must hold, namely the ratio of these mixing angles is the same as the ratio of the masses, then we explain the magic 0. So now the question is there a symmetry that enforces this relation? And it turns out that we are just one step away from figuring this out. There is another Z2 symmetry that is a subgroup of the total U6 that exchanges L0 and SC. Basically, by considering this symmetry, we see from the way the fields are rotated that these 2 mixing angles are actually related to each other in a very simple way. So upon considering this symmetry, we actually see that, okay, there's one more thing, which is the mixing angles must be proportional to the mass square differences, just as a simple fact from diagonalizing matrices. So this means that, well, if we also take into account the U1 factors, we can uniquely fix the form of theta and theta c, with n being just an overall constant that we cannot figure out the value of at this level just by symmetries. But crucially, by fixing the forms of these mixing angles in this way, we see that the relation that we saw in the previous slide is indeed satisfied, which means that we indeed will get 0 in the end if we calculate the dipole moment. So just to recap, what have we done? So we started with a toy model, and by a spurion analysis with the U1 to the 6 times psi symmetry, we can uniquely fix the form of the dipole to be the sum of these 2 terms. And then we can map this analysis onto the full model and see that the dipole is really written in this form. And then we look at an additional Z2 factor of the full symmetry to see that there is a relation between these rotation angles, and that is eventually what sets the dipole to 0. So this is the explanation in the symmetry explanation in the mass spaces.
So the Nima and KSK happen to take this particular set of parameters when they found the 0 at one loop, or?
Particular set of parameters.
So they just computed this thing, but of course they explain in terms of total derivatives,
Yeah.
but they chose this particular set of parameters to, I mean, you need to satisfy the particular relationship, right?
Yeah, so this relationship
Yeah,
is dictated by symmetry. So then the thing is, it's not the numerical values of these parameters, any specific numerical values of these parameters that has to be put in by hand. It's really the structure of the theory is such that
okay.
you look at some of the symmetries or the broken symmetries in the UV, it just tells you that these have to satisfy this relation.
Okay, thanks.
Yeah.
Yes.
This additional spurious symmetry, does it also appear in the toy model, explaining why this YL, YR?
Yeah, but you cannot show that these add up to 0. So these will be independent parameters. So I guess maybe we can go back a little bit. So the relation between the power couplings in the toy model and the full model will involve these mixing angles. So that's why by relating these mixing angles in the full model, that introduces extra correlation between the two terms. So generically, if we just look at the toy model, this is the final result. That's
Okay.
Yeah.
Okay.
It's non-zero.
So in this sense, your complete model is a bit more predictive.
Yeah, that's right. Yeah.
Okay.
All right. So any more questions before we move on to the next version of the symmetry explanation?
I was trying to remember the neutrino case where you have a very small mass correction to neutrino, but a large correction to the dipole. Right? I think some of the model has the argument that for the mass term you are including the longitudinal mode for the charged particle in the loop. For the dipole you have the transverse mode. Right? Then you have different couplings contributing to the mass and the dipole. It seems to be different case here.
So it sounds like particular to, specific to that model. So I can't remember the details, but so here is really the longitudinal W that's running in the loop, or in other words, the charged Higgs, the charged ghost in both for both the mass and the dipole.
Okay.
Yeah. All right. So. Great, so I guess for the last part of this talk, I'm going to give you an even more elegant and interesting version of the symmetry explanation, but in the electroweak unbroken phase. So we're going to borrow some insights from the mass basis calculation, which is that the key symmetry, as we saw, was a Z2 symmetry that's exchanging the L and the S fermions. And now if we look at this in the unbroken phase, this is not quite trivial because we're exchanging an SU2 doublet and an SU2 singlet. So how do we make this happen? We embed the theory into SU2 cross SU2. And in this way, the SU2L doublets will still be SU2L doublets. The SU2L singlets will be embedded in SU2R doublets. So these are the SU2R doublets in this extended model. And we're introducing these auxiliary fields that don't really play any role. There is a right-handed neutrino and there are also heavy charged leptons, but you can just decouple them in the end. And also a comment on the notation, if it's helpful in what follows, I'm going to use unprimed indices for SU2L and primed indices for SU2R, just to keep track of everything. And also, the Z2 exchange symmetry would just be what we will call PLR, that exchanges SU2L and SU2R doublet fields.
Just a short question. Is this just a technical trick that you extended to SU2R, or does it have a physical meaning that you only get it if you have a larger symmetry?
No, it's a technical trick. So,
it's a technical trick.
Yeah, in the end, we're still going to be interested in the original model.
So in principle, you could also write down some symmetry which does this transformation in another way.
Yeah, I mean, this is just making this completely transparent, right? If you have two
Yeah.
SU2s and you have a Z2 exchange in the two, everything becomes
Yeah, I
really
get this,
simple.
but I just wanted to ask because you say, okay, then in the end I decouple everything, but still it's a different theory, right?
Yeah, so you decouple everything after plugging in the spurions.
Okay.
But before that, the full symmetry structure is actually making things a lot easier.
But could you potentially write it down without extending to SU2R?
Probably you could. It's just more complicated.
Okay.
You'd say that's what you just did in the previous section, right? Doing the calculation of the mass basis.
Yeah, but that's for setting the Higgs to the valve and working in the mass basis. Yeah.
Sure.
There's that version of it, and here I really want to keep the SU2 cross U1 structure of the standard model and work in the unbroken phase without setting the Higgs to its valve. And I'm just saying, because this requires a Z2 symmetry that seems to exchange a doublet with a singlet, the easiest way to do so would be to embed the singlets into another SU2.
And actually, this explains at least one feature. In other words, the symmetry protection that you explained in the previous part, it is actually done by emergent symmetry, not actually UV symmetry. Right? If you take your original UV theory as it is, which you don't actually have this exchange symmetry, but once you Higgs the theory, then all of a sudden you can have an emergent Z2 symmetry. Then you can have a protection to.
Yeah, but there is another caveat, which is that this is only the symmetry constraint only works up to a certain order in perturbation theory.
Sure.
Yeah, I guess it can be thought of as an emergent symmetry, setting things to zero in the IR. Yeah.
Sure. Okay.
All right, so we can actually write the theory in a more compact way by introducing field multiplets, capital sign psi c, and here capital indices will just be like both prime and unprime indices. So just by putting the fields together in this way, we can write, in addition to the kinetic terms, the mass and Yukawa terms in this very compact form. So there is a mass matrix 3 by 3 containing ML and MR. So these are spurions, and these carry SU2L and SU2R fundamental indices. So this makes it, the indices make it clear how they transform under SU2 cross SU2. And under this PLR, this Z2 exchange symmetry, it's simply an exchange between these two spurions. Or I guess more generally, because these two field multiplets are related by PLR, PLR really takes this matrix M plus U to its transpose, and that's why these two are interchanged. And of course, the background values that I'm writing down here are what breaks all these symmetries.
I apologize. What is U?
Yes, that's on the next slide. So U contains Yukawa couplings. So as I said, the terms that break these symmetries would be the mass and the Yukawa. And the Yukawa is contained in this U matrix. So more precisely, it's the product of Yukawas and the Higgs. And because the Higgs, which I'm going to talk more about on the next slide, is a bifundamental. It carries two indices. The Yukawa, each Yukawa coupling actually carries 4 indices. So this is just a tensor, and we know very well how it transforms under SU2 cross SU2 just by looking at the indices. And under PLR, again, there is a very simple interchange symmetry between these different tensors or different components of these tensors. And again, the background values of these Yukawa coupling tensors break this symmetry in the UV. So finally, the Higgs, which, as I said, is bifundamental. I mean, this is something that we're already familiar with, how to embed the Higgs in the SU2 cross SU2 theory. And importantly, we can write down the U1 ENM coupling of the Higgs and introduce yet another spurion, which is the electromagnetic charge, which also carries 4 indices because the Higgs is a bifundamental. Okay, there is one more trick before I can do this spurion analysis, which is we want to make a field redefinition to make our life a lot easier. And the field redefinition is a rotation for these field multiplets. And we're going to choose unitary matrices which depend on the Higgs field, such that this matrix n plus u is, in a sense, diagonalized. So this very naturally relates to what we did in the mass basis. So in the mass basis, if we set the Higgs to its value, then this, what I'm showing here, is just diagonalizing the mass matrix. But now we don't set the Higgs to its value. We work in the unbroken phase. So this becomes a Higgs field dependent field redefinition. But it serves the same purpose as to simplify the structure of the symmetry breaking terms.
Sorry, is it non-anomalous field redefinition? So okay.
So all these are these.
Presumably it takes some form of e to the I, some theta h type, that kind of form, right?
Right. I mean, this is the theory with vector-like fermions.
Okay, then yes.
Then
Thanks.
I guess you don't really worry about that.
Yeah, thanks.
Yeah. Good. So the n plus u, the symmetry breaking piece, is greatly simplified by this field redefinition. But of course, there is always a conservation of difficulty, I guess. The kinetic terms will become messier because once we make this field redefinition, we obtain some extra terms. And these are actually some derivative operators. And what we have done is really we have rotated away the off-diagonal Yukawa couplings, the non-derivative Yukawa couplings, and we have traded them for derivative couplings. And this will be very important in what is going to come next. So yeah, this is the spurion analysis in the new basis. So we can, upon this field redefinition, work out what new operators are generated from the kinetic terms, and up to the order that will be relevant, there will be dimension 5 operators with coefficients C5L, C5R, and dimension 6 operators, C6L, C6R. And they're related to the spurions in the original theory, the mass and Yukawa tensors, by these equations. So yeah, this just involves some careful keeping track of all the tensor indices that reminded me a lot of the GR homework. But yeah, so this is a well-defined procedure. In the end, of course, all these indices are really telling us how everything transforms under SO2 cross SO2. And that information is always clear throughout this calculation. And then we only have to worry about this extra Z2 factor, PLR. And its action is also very simple, which is just to relate C5L and C5R, C6L and C6R, just by the way that these parameters are related. So now, finally, we're in a position to build a dipole operator from all these spurions. So the goal is to build something like this. And we need to figure out the product of spurions that can contract with all of these indices that are carried by the fields. And the ingredients we have are the mass spurions, the electromagnetic charge spurion, and these dimension 5 and dimension 6 coupling spurions. And all of these are tensors carrying SO2 cross SO2 indices. And there are several constraints that we need to impose for this spurion analysis. So first of all, actually instead of SO2 cross SO2, we can consider 4 factors of SO2 cross SO2 that act separately on these different flavors of fermions and also the Higgs. So very conveniently, I have introduced different colors for these different SO2 cross SO2 factors. So all we need to do is keep track of the colors and make sure only contract the same color indices. And then we also have to take into account the fermion number for each flavor, the 3 factors of U1. And there is a PLR, which are these transformations that are very simple to impose. And we're looking at one loop dimension 6 operators, which means by dimensional analysis, H-bar counting, we know it has to take this form, and there's also no logarithms. And finally, there is a constraint because this Higgs, the external Higgs, does not carry a derivative. So eventually, if we go to the broken phase, this has to be set to its value. So this means there cannot be a derivative acting on this field. So this actually sets a very strong constraint on where this Higgs field can come from. And in fact, as I was highlighting a few slides ago, we're trading some Yukawa couplings for some derivative operators. And for all these derivative operators, as long as there is a derivative acting on the Higgs, we cannot use that Higgs as the external Higgs. So the only possibility is that the Higgs has to come from these specific indices from these spurions. So imposing all these constraints, we end up with a unique possibility. So it's given by this equation. So it's again the sum of two terms that are related by PLR. And I guess you can already see this very explicitly. I mean, for each of these factors, it's what is L and what is R. That's just how things are related. We can also understand this from the corresponding diagrams. So it will be these sets of diagrams in the new basis. So these, the three diagrams in the first row all have the same spurion structure as in the first term in this equation, and same for the second row. So these diagrams are related by PLR, as do these two terms. So now, I mean, I've told you we have fixed a unique form for the dipole operator. And why is this 0? To see that this is 0, we just need to substitute in the background values of the spurions, which, I guess as I was trying to emphasize, is really characterizing the way that this symmetry in the UV is broken. And once we do that, we obtain this very simple looking combination that as a generic tensor does not vanish, but the background values of these spurions turn out to be just this simple difference between these two terms. And the cancellation is really dictated by this PLR symmetry that's relating these two terms. So yeah, this is the YD prime piece. There is another piece that depends on the other Yukawa coupling, and it follows a similar analysis, although it's a little bit more tedious, so I decided not to show that. So in the end, let me also briefly mention what happens to the mass. I guess I was trying to make a comparison between mass and Yukawa, and here, so mass and dipole, and here we have a vanishing dipole but a non-zero mass. So what does the spurion analysis have to say about the mass, or the Yukawa operator really, the dimension 6 Yukawa operator in the unbroken phase? So we can do the same spurion analysis to figure out the combination of spurions that is consistent with the Yukawa operator. So it looks slightly different. It will involve some logarithms, and also because the mass dimensions are different, we have to put together the spurions in a slightly different way. And in the end, instead of this simple combination that you saw on the previous slide, which will turn out to be 0, we have a different combination, which upon inserting the background values is given by this expression. And this is exactly what we find in the explicit diagrammatic calculation. So this is to say, the spurion analysis does not only tell us that the dipole has to vanish, it also tells us the correct form of the Yukawa operator. So all of this is just by a symmetry analysis. Yeah, to recap, what I just showed you is, in the last part of the talk, is the unbroken phase explanation of the magic 0. And there are, the key is a PLR, a Z2 symmetry, and to use it, we need to embed the theory into a larger theory, which features SU2L cross SU2R, and the field multiplets are related by this exchange symmetry. And the trick is to perform a field redefinition to go to a new basis where there are a lot of derivative operators. Lower dimensional non-derivative operators are traded for higher dimensional derivative operators. I guess equivalently, we can say that we're applying the equation of motion in a very specific way. And this is perhaps not the most familiar way that we use equations of motion. In the following sense. So here I'm just showing a simple example of a 5-4 theory. The equation of motion can write it in this way, and the way we usually use the equation of motion is by trading derivatives for the non-derivative operators and lower dimensional operators. So, for example, this is what we do when building up an operator basis, say in the standard model EFT. So first we write down all the renormalizable operators at dimension 4, and then we go to dimension 6. At dimension 6, if we encounter something like d squared phi, we replace it by these terms. So then the first term will just be a dimension 4 term that's already present in our dimension 4 basis. And then we'll have some other dimension 6 operator that doesn't have derivative. And then we move on to dimension 8. So the thing is, once we establish a basis at dimension 6, we do this at dimension 8, it will give us some operators that we already have in our dimension 6 basis, and then some non-derivative or less derivative operators at dimension 8. So this is a systematic procedure that we can carry on to higher and higher dimensions. But here we are doing this, we're using this equation of motion in a different way, in that we're trading this lower dimensional operator for some higher dimensional operators with either more fields or more derivatives. And this is particularly useful in this case because once we ask what kind of spurion combinations can we put together, the fact that we have either more fields or more derivatives is actually putting a lot of constraints on what we can do with the spurion analysis. And that's really perhaps the most important lesson for this trick. Yeah, so that's basically the end of the talk. Just to repeat the key concepts, symmetries in the UV can lead to selection rules in the IR. Symmetry breaking in the UV can also lead to selection rules in the IR. And I have showed a spurion analysis that reveals the hidden symmetries behind the recently discovered magic zero in both the mass basis and gauge basis analysis. And I think overall the lesson is perhaps, I think it's really exciting to start with a phenomenology problem, say the muon G-2, and by looking at the models and we observe something that is really interesting, and then we uncover some underlying theory structures that gives us a better understanding of the theory. So this is what I find really interesting. So I guess that's the end of the talk. Thank you very much.
Can you rotate it again? Wow.
Thank you, Kevin. Yeah, I like your ambigrams.
So I guess, I don't know if CP violation can play a role here, but so it would be interesting to find a magic zero for the electric dipole moment while giving a contribution to G-2, for instance. Then, because those operators are quite related, right? So,
yeah, I mean, it's just the real imaginary part of the same operator.
Exactly.
Right?
So
yeah.
Can you imagine that something will give a zero to imaginary part?
Well, I mean, these have different CP properties, right? So
Right.
I guess it wouldn't be too difficult. If the UV theory doesn't contain a physical phase, then I guess we just don't get an EDM.
Yeah, that is
That's that's a symmetry.
good.
So I guess Carlos is looking for other ways.
Yeah, other ways.
Of
Yeah.
cancellation.
Yeah, it's kind of a little bit orthogonal to the direction we're going here, because here it's just looking at this one operator with a generic complex coefficient. What are the symmetries that can set this to 0? So this is kind of the idea.
But this looks, looks very concrete, but also you analyze only this example, this particular. I don't know if you have other examples, interesting examples.
Yeah, obviously it will be very interesting to extend this to other examples.
Maybe a related question, can you somehow reverse engineer this? So you say, I want this dipole operator to be 0, what type of models can I build?
Right.
Yeah, the inverse magic zero problem. Yeah.
Can you imagine that this is possible, or?
Yeah, so the thing is, I mean, it's
Let's say we want to enhance MW, but we don't want to touch other things.
So I'm confused a bit by the takeaway lesson, or I don't. I would have thought that, if we write down we define our fields and representations and such, we write down all of the operators consistent with the symmetries, and then do some spurion analysis. Why should I expect to get mileage? Why should spurion analysis be so basis dependent, or
It's not, well, as we know, all the results will not be basis dependent. It's just that certain bases are easier for the analysis. So I can get into a little bit more detail on why we want to do this basis transformation. So in the original basis, there are off-diagonal Yukawa couplings, meaning there's a Higgs and there are two heavy fermions. They're different. One is L and the other is SC, for example. So that means when we draw a loop or when we put together spurions, we will get something that will correspond to a loop involving different flavors. So for that, importantly, the constraint of the no logarithm will be a lot trickier, because here in the new basis, we only have one mass running in the loop. So if there is no log, there is no log. But if there are two masses, we know it cannot have log mu, but it can have log of ml over ms. So those kind of terms we cannot get rid of if we don't do this field redefinition and remove those off-diagonal Yukawa couplings. So that's basically the.
Also, it's kind of standard tech trick that you always want to diagonalize the like Yukawa or mass term. Then you can just simply cleanly integrate out the heavy state, because now you just have a clean mass instead of interaction term.
Right.
Then you have to have this derivative term, but in your case, basically you can say that I don't gotta use that for I mean, in some circumstances, in the last bullet point, right, derivative terms doesn't matter.
Right.
Okay.
I guess I would have said I thought about spurion analysis as being just sort of group theoretic data.
Yeah, it is.
True. It's just that depending on the choice of basis, you have a different set of symmetries you have to keep track of. Therefore,
well, I guess it might be a little bit cheating to say it's a purely symmetry explanation, because there is an additional input, which is that there shouldn't be logarithms. I mean, that has to do with.
That's field theory.
Yeah, that's field theory. So it's not just group theory, it's a little bit of field theory as well. And it's just that the way we're able to use this field theory information in combination with the group theory information is different in different bases. And in one basis, it's possible to carry through this argument, and in another basis, it's not.
well, maybe in the particular sector that you're focusing on, you might have some polymorphy that you know that logarithmic cannot be generated.
Yeah, that's another possibility, yeah.
Also, I have a question about in your slide 32. Good. Right. Oh, wait. I thought no 30. You had when you wrote down the expression, general expression for the dipole.
There is a mistake in that index. No, I'm kidding.
Sorry, the general expression for
The dipole operator.
the dipole.
Yeah. I think.
Oh, the mistake is
No,
still in this.
before you set things to the VAV value,
Right.
you had the expression. Yeah, here. Good. Thanks.
Okay.
Right. So good. So this general tensor expression, the red box, generically is not zero.
Right.
Only if you take the limit of vacuum expectation value, you get a zero.
Yeah.
So to me, I still interpret this as an emergent symmetry. So in other words, even if you impose a P and R explicitly in the UV, you can have a non-zero dipole. But only if you go to the VAV,
Right.
all of a sudden at that point you do have this symmetry, right?
Yeah, but
So in
it
a
don't-
sense, I guess what I'm trying to say is that it's not actually SU2 cross left, SU2 cross right, cross P and R actually dictates the zeroness of the dipole. Indeed, you can have a non-zero, right? If you go down and settle down at the specific point in the moduli space or VAV.
Right, yeah, I agree. I mean, this symmetry analysis is really telling us the specific form
Yeah.
of the dipole.
Okay.
And why it's zero. It doesn't say about anything about that yet, but
Yeah.
because of the way that this symmetry is broken, the way
That's right.
we choose this particular point in the
Right.
in the theory, or in the enlarged theory. It's not really the theory space, because ML and ML, MS, these are generic parameters. We're not setting numerical values of these parameters.
Yes.
Yeah, but it's just that the tensors, the spurion tensors have this background structure.
Yeah.
That's giving rise to the zero.
Yeah, I just feel that there seems to be more to be understood about this error part.
Yeah, I agree, yeah.
So because that has the biggest magic happening, right? I mean, this is great. So basically, you provide us language to keep track of it. Now there's a last part where we actually get the magic. Fantastic.
Any further questions? Can thank Kevin again. Yeah, really interesting. Fantastic. Thank you. Let me.
You.
No, it's
It's me who took that.